We are going to start the last session of the day, which is focused more on multimodal approaches. And it's my pleasure to introduce my colleague, Anoop Cherian from MERL. Anoop's a principal research scientist at MERL. And before that, it was at the Australian National University. Yeah. Before that, at INRIA, actually, in France, which I only discovered lately. And he's been doing super exciting work on neuroscene representations for multimodal machine intelligence, which he's gonna talk about today.
Okay. Thanks, Jonathan, for the nice introduction. And hello, everyone. I'm Anoop Cherian. I'm a research scientist at MERL, and today I'm going to talk about neural scene representations for multimodal machine intelligence. And this is joint work with a lot of colleagues at MERL and several of the interns over several summers. So it's kind of the work that I'm going to talk about is something that is done over the last 2-3 years. To start with, so the world around us is essentially multimodal. I mean, there is a lot of things happening in different perceptual modalities. For example, it could be speech, vision, audio, physics, geometry as in the 3D sense of the world. A lot of things, a lot of modalities are important to understand what is happening in a scene. And for example, if you see this video, I don't know if you can hear it. Let's see. And if you ask the system a question, why did the book drop? Now it's not just the vision or the sound. You have to understand what is happening in the scene, the interaction between the kid and the book, and the third sound that you would probably decipher when that book fell down. So all these different information spread across different modalities have to be integrated to come up with an answer to this kind of a question. So because a baby kicked it, this is an ideal answer that we would want from this multimodal integration of perceptual modalities for solving this, or kind of coming up with an answer to this question. So the big research vision that I have is to kind of integrate a lot of different modalities, or the information spread across different modalities, into a comprehensive reasoning pipeline. For example, it could integrate vision with audio, text, language, touch sensors, or depth. All these different modalities have to be integrated and for solving several real-world tasks. For example, audio-visual question answering, or it could be vision and tactile sensing, or it could be audio-visual embodied AI. Some of these problems I will touch upon in this talk. And so the idea is what could be a potential integrative framework that can plug in these different modalities and can reason across modalities for solving real-world problems. So that is kind of the big picture that we are at MERL are trying to build upon, or build for solving several problems. So in this talk, I'll describe one of the basic building blocks, which we found is very useful for having this kind of an integrative approach, which is called scene graphs. And I will talk about applying applications of these scene graphs for problems such as audio-visual scene-aware dialog, which combines audio, vision, and language models, or visual question answering, which combines vision, language, and geometry, as in 3D sense of the world, or audio-visual source separation, which combines audio and vision, audio separation and motion prediction, which combines audio, vision, and depth, or a recent work that we have been excited about is this called AVLIN, which combines audio, vision, language, and embodied navigation, or embodied AI. So to get started, I will describe the basic framework. I mean, what is the challenge that we are trying to solve at a fundamental level? So you are given a video sequence and you have an associated audio for that, and you are asking a question: what is the man doing in this video? To answer this question, we need vision, perhaps, but the vision is not probably enough. For example, vision can give us object detections of the person. There is a cup that person is holding. And then there is a dynamics information. Maybe the person is shown to pour something, but then is it actually the liquid is flowing through? Maybe the sound can help us, understand that there is some sort of a sound of pouring that is happening. So all these different things have to be aligned to come up with an answer to this question. So that is where this multimodal alignment is important to kind of come up with an answer to a reasoning sort of a problem. And there have been a lot of interest in this kind of a multimodal alignment, but many of these methods that when we started working on it, some of those methods that I'm listing here, they were essentially integrating, plugging in audio streams, video streams, and other modalities into a gigantic neural network, and then the alignment happens implicitly, and it's such an implicit way of learning perhaps needs a lot of data for the model to kind of extract the correlations between modalities. So we thought maybe there is a better way of doing this, and that is where the idea of scene graphs came into picture. So scene graphs are visual scene graphs. Scene graphs are essentially disentanglement of a visual scene into its essential components or ingredients. For example, in this case, there are you can run an object detector on this image, and then it can detect parts of the scene. For example, the bat and the girl, and maybe there is a attribute recognition algorithm that can extract attributes. For example, the color of the bat or the dress of the girl, and so the scene graph allows you to disentangle the scene into multiple smaller components, and allows you to kind of hierarchically decompose the scene into whatever kind of desired granularity you would want to kind of solve your problem. For example, if it's a question answering task, depending upon the question, you can actually get into the right granularity and extract the corresponding features to kind of come up with an answer to the problem. So we found this to be an extremely interesting data structure to solve, or to kind of encode your visual scene, so that you can move away from reasoning at the pixel space to reasoning at a much more semantic, higher level semantic scale. And the other side of the story is that if you have your scene decomposed into graphs, then there is a lot of technology out there which uses graph neural networks for a lot of other problems. For example, what are the most important nodes of a given graph? We can use node convolutions to find out or extract out such important nodes in the graph, or you can use edge convolutions to extract out important edges. So these operators are extremely useful for kind of decomposing your graph into its essential components, which are important for a given task. And so with that setup, I will talk about this, the first problem that we actually kickstarted this whole investigation into this multimodal integrative approach, which is the audio-visual scene-aware dialog problem, where we combine audio, vision, and conversational AI for solving this dialog problem. So I'll start with a brief video, which is an application that we developed at MERL for driver assistance system. And just let me play the video.
Our scene-aware interaction technology is also capable of adjusting its output based on a spoken response from the driver. For instance, if the driver indicates that they cannot see the given landmark, the system will quickly identify alternate landmarks or improve the guidance sentence to provide a more detailed description.
Follow the silver car to turn left.
I can't see it.
Okay, follow the silver car in the leftmost lane.
So that is setting for human-machine dialogue. And this is more of an application setting, but then in order to study this, you need to have some data set. So we defined this task of audio-visual scene-aware dialogue as the task of given as input a video sequence and its corresponding audio. There is a caption associated with this. For example, it could be a description that you see in a YouTube video, for example, and then there is a dialogue. The dialogue is essentially two people talking about the content and audiovisual content of this video. And then there is a question, which is perhaps the last question in a dialogue that one person asks. And then the system has to analyze the audio, video, the captions, dialogue history, question, everything together to come up with an answer to this answer to this last question. And why is this dialogue important? Because the dialogue is there could be references. For example, in one of these questions, that in the dialogue, the person might ask the name of the person, but then he will refer to that person as he or she later. So if you have a question in which it's referring to a he, you have to understand the dialogue and the context and everything to come up with an answer to that. So this is a task which covers a lot of different kind of data modalities, and it's a lot of information. You have a large data set. So how do you kind of integrate all these information for kind of reasoning? That was one of the motivations for looking at this scene graph problem. And so in this particular dialogue setting, what are we expecting as the output of this of a reasoning algorithm? There are two variants. One is that you have to select one of the answers from a set of candidate answers. We have 100 different answers, of which one of them is correct, and you have to select one of those answers. So it's a kind of visual question answering kind of a setting. Or there is another variant of this where you have to generate a free-form answer given this question. And so, like I said, this is a very complex problem because there is a lot of modalities involved, and there is a lot of information in videos and audio and everything. So how do you decompose it? And the way we thought about it is to kind of do the abstractions of this video modality in a hierarchy. For example, come up with object level representations, which can then be integrated into frame level representations, and then integrated into video level representations, such that if you have a question that is asking about something at a different a specific granularity, you can actually have representations of all this out there in some latent space, and then you can get to that in a disentangled setup for extracting the correct answer. And then once these feature vectors are extracted from these different granularities, then you combine it with the encodings of the dialogue history, which is text, and then other modalities, for example, audio, and combine it with the question embeddings to produce answer. So this is the overarching pipeline that we have. And to get into the specifics, so the videos are essentially represented using neurosymbolic representations using scene graphs. So you run an object detector, so it can detect, so we have an object detector which is trained on like visual genome data set, which is having like 1,600 classes. And these classes kind of encompass many of the daily life objects that one would encounter. And then there is a visual relationship detector, which we run on these object detector outputs. So visual relationship detector takes two object nodes and can predict what is the potential relationship between these two nodes. And that forms the edges of the graph, and the object detector outputs form the nodes of the graph. So you have a scene graph essentially. And then you can do all your reasoning using graph neural networks on the scene graph for producing an answer. So this is the pipeline that we have. So you run these object detectors and the relationship detectors on every video frame, producing a scene graph for every video frame. And then, so you have one scene graph, typically like the graph has about 40 to 50 nodes. And then you pass these graphs into an intra-frame reasoning, which is what I mentioned before, the frame level representations, because you cannot really work with these graphs for every video frame because there are so many nodes. So you have to kind of compress it in some manner in some latent space, and that is what the intra-frame reasoning does. And then inter-frame reasoning, which is the video level representations that you create from this. And then you have representation, one feature vector for every video frame, and that you combine with the audio feature vector from that corresponding time-aligned frame to create audio-visual memory. And then you combine that audio-visual memory with the dialogue history using transformers and captions and question generation module, question encoding module to produce an answer or retrieve an answer from a set of candidates. So that is a kind of a pipeline that we have. And this pipeline, I would say, is kind of the basic setup that we kind of expanded for a lot of other problems. For example, in this case, the audio is actually augmented with the video at a later phase. So what if you actually move this audio fusion to a phase which is before the place where we have here? So for example, here, this is a video level or clip level audio concatenation. But if you move this audio part to an earlier phase, then that leads to audio visual source separation, which I'll talk about later. So this was a basic framework that we started off for looking at this problem. And so this I just mentioned. And so to study this problem, there was no real data set which has scene-aware dialog in it. So with several of my colleagues at MERL, including Chiori, who was leading this, we collected this data set called audiovisual scene-aware dialog, which is built on the public data set called charades. So the way we collected this data set is that you have a video sequence, and two people are tied to this data set. One person can see the whole one video, other person can see only part of the video. And the person who cannot see the video completely can ask questions to the other person to understand the video better. So that kind of creates a dialogue, and that dialogue is what we use for analyzing the performance of our algorithm. So these are kind of daily living situations, and there is not much of a camera motion, I would say, but there are camera motions like you can see here. And there is no real background sound. So the sound is associated with what the person is essentially doing. So it was more or less a clean kind of a setup, but then it's challenging because it's kind of the daily living situations that this data set covers. And so we applied the kind of framework that I just mentioned with scene graphs. And for example, in this case, there is a caption and then there is a video sequence. And the question is, what room do you think this person, this event is happening? And it can generate either a free-form language answer, like it looks like a laundry room. You can have a beam search and create varieties of different varieties of these answers. Or it could be a retrieval task where it selects one of these answers, and like our system does here. And so this is just a hand-picked example, but then we actually have a quantitative analysis of this performance. And we find that our framework leads to state-of-the-art results. And SGSGR, which stands for spatiotemporal scene graph representation, is better than other methods, like I mentioned, where they use transformers to kind of concatenate everything to do the reasoning. And combining with audio gives a performance boost as well. So the table below is called the mean rank. So out of the 100 different answers, candidate answers, you select the best answer, and what is the rank of that best answer among all the answers, all the retrievals in your data set. So that's the mean rank, and lower the better. So ours is better. And we also did some analysis to understand whether scene graphs are really useful for this task. So we replaced all the scene graph parts of the framework and replaced it with I3D features, which are video features or dynamics features. And we found that the system is not able to learn anything significant if you don't really disentangle the scene as scene graphs, because you have once you have the disentanglement, it allows you to it's like a language model. You have the words, and if you have the words, you can correlate with things in the scene much better than if you have everything into some implicit embedding space and you want to find what is correlated with what. So scene graphs allows you to kind of disentangle things. So I said the correlations are more apparent. We also did some analysis or a human study on the kind of answers that the system generates for the dialog question, and we find that our performance is better than other methods. So that concludes that part of the talk. And the second part is basically trying to address some of the problems that we encountered when we did this AVSD problem, that is audiovisual scene-aware dialog problem. And so the idea is to actually combine vision and language with geometry. So this is the pipeline that I just mentioned. So you have a video sequence, and you take all these video frames, construct scene graphs for every video frame, and then do all these graph neural networks to produce a representation for retrieving an answer. But one of the key problems here is that you have to have these scene graphs generated for every video frame, which is expensive and redundant, because several of the nodes in the graph won't change from frame to frame. For example, here, the refrigerator, that node is just repeated. And that is, I would say, an artifact of the camera, because camera is capturing the scene as one frame at a time, whereas the scene itself is not really changing. Only some things are changing. And so that is an artifact of the way we kind of use the camera system. So why would we necessarily need to stick to that? Why can we just avoid this this redundancy in the semantic representation and get a much better representation for reasoning? So that was a thought, and one of the ways to tackle it is to understand the scene in its 3D sense. So the world is 3D. So what if we actually induce 3D into our representation space, such that our scene graphs are kind of 3D. But then if you arbitrarily download a video from YouTube and wants to construct 3D, that's impossible, because you don't know the camera parameters, you don't have multiple views of the scene, so it's impossible to do it. But then there is a lot of progress in monocular to 3D reconstruction or depth reconstruction, which we call 2.5D. So for example, here this is just one frame, but if you use monocular to depth, that kind of can estimate the 3D sense of the world from just one camera view or one frame. So what if we actually use this technology to come up with building a 3D sense of the world, and then you can create 3D scene graph, and then we can do a better way of disentangling or kind of inducing the 3D into the reasoning pipeline. So that was the thought. And so, like I mentioned, 3D scene graph could remove the redundancies, and objects disentangled from their views could help with occlusions. For example, if the camera is just moving a little bit, maybe an object which was there in the scene becomes visible in some other camera view. If you register all these frames together into a one 3D model, then you can have graph nodes, which corresponds to the things which were occluded in one view, but still there in another view. So it leads to occlusion reasoning. And it also leads to removal of redundancies, implies like you have a smaller graph, so you can have a sample efficient learning of this whole inference pipeline. So this is kind of the pipeline that we kind of derived from our ABSD pipeline. So here you have a set of input video frames, and then you transform every video frame into a 2.5D representation. And then you decompose the scene into a static set of frames or static set of nodes in the graph, which corresponds to things that generally don't move, for example, a table or a tree, and other things in the scene which can move, for example, a car or a person. And you disentangle this such that you can register the frames together only on the nodes that corresponds to things that don't move. For example, you can register the tree from different camera views, or maybe if the camera moves from different point of views of the camera, you can actually register the points corresponding to the tree, and then put all this together. So all these different frames together, such that you remove the redundancies in your object detector detections, basically, or the graph nodes. And dynamics, the dynamic graphs, so that is corresponding to things that move. For example, if the scene is static, and if I approach to take this water bottle, all the graph nodes corresponding to me and this motion is all corresponding to the graph nodes in the dynamic graph. And then we can use some sort of like what I call hierarchical 2.5 plus 1D transformer to do some integration of these different the features from these different embeddings to create an answer. Now, so the basic thing is to start with is to take the video frames and then convert it into 2.5D representation using and so the way we essentially does an object detector, and the detected nodes are kind of superimposed on these depth maps generated by this monocular to depth generation algorithm, and have a 3D coordinate of each of these nodes of the graph. And then once we have that, we use this in this hierarchical 2.5 plus 1D transformer So this is essentially a standard transformer, but then there is a caveat. So the basic difference from a standard transformer is that we have some idea of the 3D or how interactions happen in the scene. For example, in this case, let's say this brown node is a static node, for example, this table, and the green node is a set of nodes corresponding to my hand moving towards this bottle and picking it up. So as the time progresses, you can see that the distance from the dynamic node to the static node decreases and then increases. So that is where the interaction happens. And if we have a way to if we can combine this interaction in a spatiotemporal manner, capturing like the spatial interaction, for example, the space between my hand and the bottle is decreasing and then increasing, and the time at which this happens is captured in this at the same time this interaction is happening, like the bottle is moving and my hand is moving. So this the spatiotemporal proximity is captured in this kernel metrics. And so the idea is that what if we actually use this kernel metrics within a transformer? Why would we do that? Because if we look at this transformer query key attentions, it's essentially some sort of a linear kernel in a latent space. So what if we replace that linear kernel by RBF kernel, but then the embeddings for that kernel is actually coming from the spatiotemporal information from the world, the physics of the world. It's not like an embedding. And so then you can actually combine the interactions in the real world with the embeddings in the latent space to create a spatiotemporal transformer that can combine both the latent space interactions as well as the real world interactions to come up with a much more richer representation for different tasks. So that was the idea. And one of the key problems or key ingredients here is how do you define this the granularity of the interactions, and that is controlled by these sigma values, the bandwidth of the RBF kernel. And if the sigma is large, which means that a lot of small interactions are not really important, but we are looking at large interactions. And sigma small means that you're looking at fine-grained interactions. So depending upon the question in your VQA task that you want to answer, these different granularities are important for the kind of questions that are there. And so we don't know what kind of questions are going to be asked. So we kind of do a multi-scale embedding. So at some scales, you have smaller interactions, and then you have a different sigma for which you have different interactions, and then you concatenate it into a hierarchical transformer architecture that does this reasoning at different scales. And so we applied this for the VQA task on 2 datasets. So one is the NextQA dataset, which is a very recent dataset, which contains questions which are more abstract, like, for example, why is something happening, or where is this happening, sort of thing. And then AVSTQA is our own dataset that we collected, which I mentioned in the last project. And we find that using this hierarchical transformer with this 2.5 plus 1D representation leads to significant improvements. Like we have about 5% improvement in the accuracy of retrieval of the correct answer from the set of answers. And more interestingly, we found that it is is significantly better in retrieving answers with more abstract questions like why or how, and which is probably not really something that people have looked at in computer vision literature before to kind of come up with architectures for higher level reasoning. So that I think is pretty impressive. And so we have state-of-the-art results on this dataset as well as on AVSTQA. And we also did a lot of analysis to understand what is really going on within this huge transformer architecture. We find that, the ablation studies revealed that different combinations are important, but then the whole architecture itself is important for getting the best performance. And we find that this redundancy removal leads to nearly 50% reduction in the number of graph nodes in this whole pipeline, that it's more sample efficient in learning on the task. So here are some examples of qualitative examples of the kind of results that we can produce. For example, the second one, where is the baby while it was fed milk, and you have a bunch of answers, and ours says that it's in the ladies' room, and then HGA is a state-of-the-art model which has a different answer. There are a lot more examples in the paper, but yeah. So this just says that it has better understanding, perhaps. I mean, understanding could be an abstract term, but have better performances in this task, on this task. So now moving on, like another task that we looked at is this audiovisual source separation. Here, the problem, I think most of you are familiar, but just to recap. So you are given a video sequence, and there are some audio sources in this video sequence, and then you have a mixed audio, and the goal is to actually use this video information to guide an audio source separator to separate the sources. And our algorithm is called audiovisual scene graph segmenter, because we use scene graphs to represent the visual scene, which leads to the separation. So what exactly is this scene graph going to do here? So like I mentioned in the previous few slides, so you have a scene graph that captures the context of things in the video, and then there is and in this case you are given a mixed audio. So the question that we ask is, can parts of this can parts of this the scene graph, which encompass a lot of things in the scene, is there a sound associated with a part of the scene graph? And can you segment the scene graph such that that segmented scene graph can induce a separation of the corresponding audio in your mixture of audio? So in this case, say you have two sounds, like the yellow sound and the brown sound, and the part of the scene. So you have a scene graph, which is a spatiotemporal scene graph spanning the whole video. Can you find the part of the scene graph that corresponds to the yellow sound marked region, and the one corresponding to the brown? So why would you use? So we call this an audio-visual scene graph, because you are essentially associating parts of your audio corresponding to parts of a scene graph. So so that is why the association it implies the kind of audio-visual scene graphs, because every subgraph or some subgraph of the video is associated with its corresponding audio in the mixture. So why would this scene graph be interesting for this? Because scene graph kind of captures the context of things happening in the video. For example, a person, if there is a guitar in the video, but if there is no one next to the guitar, then probably the guitar is not played. Maybe you cannot really look for the sound of a guitar in an audio mixture, because the context is not really suggesting that the guitar is being played. And there are other situations. For example, the sounds are produced by an object by itself, like for example, a person speaking, or it could be a sound captured by interactions, like for example, a ball falling onto the floor and bouncing. So the interaction between the ball and the floor is causing the sound to happen. So the scene graph is probably a natural way to encode it, because the sounds that are produced by objects by themselves, that could be the node level sounds. Interaction sounds are kind of maybe captured using the edges between two nodes. So maybe a scene graph can allow capturing the kind of correspondence between audio and sound much better. So that was the intuition. And so to come up with this, I'll come up with a framework for this. So we started off with a mix and separate sort of a pipeline, where you have a mixed audio spectrogram, and then there is a autoencoder sort of a framework, which can generate a separated mask which can separate the audio from the mixture. Now, usually what happens with this kind of a setup for visually guided audio source separation is to plug in a visual stream or visual encoding of some object representation into this mix and separate framework, so that that visual feature can pick out corresponding audio. And when you train this, there is a co-learning of the audio and the corresponding video or video feature in this, so that will allow us to pick out the corresponding audio spectrogram part corresponding to a visual feature. In this case, we removed that part and replaced it with a scene graph, spatiotemporal visual scene graph. So we took out, we kind of ran object detector on the video sequences, and take out all the object detections and construct fully connected visual scene graph on this video. And then we do something called a graph attention using an RNN. So this is essentially implementing graph segmentation algorithm. But I would say it's more of a neural graph segmentation, where each iteration of this RNN will extract out part of the scene graph corresponding to an audio source, and then use that to separate the audio from the mixture. So to give a better explanation of this, so you have a video sequence, and you have a graph constructed on the video sequence, and one iteration of this RNN will take out one subgraph of this fully connected graph and produce an embedding Y1, for example, which corresponds to the man and the xylophone. And another iteration of this graph of this RNN produces another subgraph corresponding to the flute and the person, and then maybe a third one corresponding to the drums and the person. But then there is the person is not really standing next to the drums, but then it could potentially generate that kind of an embedding. And then we assume that, I mean, so one of the problems with this is, how do you know that this RNN has not generated a Y2, which is equal to the Y1 in a previous iteration? So we have to make sure that the number of times the corresponding feature is created is unique. So we kind of impose an orthogonality between the feature embeddings that are produced. And orthogonality means that if Y2 is produced, then Y2 has to be different from Y1, or Y1 transpose Y2 has to be close to 0. And then we use these feature embeddings into this audio separator network to create a mask, which is then used to separate the audio from the mixture. And we do the same thing, and whatever doesn't have a feature embedding corresponding to it, that goes to a background class. And in order to train this, we used, like I said, orthogonality loss, which ensures that these embeddings are unique. And then there's a consistency loss, which says that objects which are present in the scene graph, if that is a potentially sound producing object, then there is a class that is activated if you separate the corresponding sound. For example, there is a flute in your detection on the video side. Then there is a potential detection from the sound as well. Like the separated sound, when you pass through a neural module, produces a classifier output that corresponds to that sound of the flute. And then if you add up all these separated sounds together, then that corresponds to the mixture of the sounds in that particular video, which we use in the cut and make in the mix and separate framework. So that's the consistency that we enforce, so that the separation, if you add them up all together, you create the original audio that you started with. And when we did this, we found that using scene graphs to capture the context of the scene leads to a significant improvement in the performance of the separation. And as measured by STR, SIR, and SAR, I mean, these are the kind of metrics that previous works used to measure the performance, and we kind of used the same pipeline for reporting our performances as well. So I have some example demonstration of this.
This will be all
So I'm showing the graph, the part of the graph corresponding to the sound that is being separated as well in the middle column.
Photo. Et c'est rouge. Putain. Bravo. Oh, c'est... Ça peut mourir, c'est là et tout. Photo. Et c'est rouge. Putain. Bravo. Oh, c'est... Ça peut mourir, c'est là et tout.
Yeah, so that was the idea of using visual scene graphs for audio-visual source separation. Now moving on, we thought to build upon this audio source separation, but using more interesting visual information in the scene. So one of the ideas is that you have the scene is not, like I mentioned before, it's not just 2D. There is a lot of 3D information in the scene. For example, just to exemplify or contextualize this setting, so as you can see, and here, there is a lot of information in a 3D sense in this whole scene. Even though it's a single channel audio, you can actually have a sense of this train moving towards you, or towards a microphone as a train comes. And can we actually leverage this 3D sense of the world to kind of do a better job in audio source separation? So that was kind of the insight for this work. So you can start off with the way that I was describing. Start with the scene and decompose the scene into its constituents, like the train node. There is a rail node and the trees and clouds and all other things. And then there is a sound associated with the train. And like I mentioned before, you can associate the sound of the train with some node of the graph to construct or kind of align them for sound separation. But is that all? Maybe there is more to it, and that is the 3D sense of the world. The train was moving towards you, so that could have induced some sort of a property in the spectrogram so that you can actually have the feel of the sound is moving towards you. Can you leverage this insight to kind of do a better source separation? And for that, you need to know what was the 3D sense of the object that was moving towards you. For that, you can actually use this monocular to depth representation that I mentioned before. So what we did was we start with the video sequence, and then we computed the pseudo depth or 2.5D depth map of the scene. And then you compute the optical flow, and you superimpose optical flow onto the 3D depth map to come up with a direction of a kind of an approximate direction in which this object is moving. And once you have that, you can plug it into audio separation and motion prediction framework, for example. So that is essentially doing what it is essentially doing is you have the video sequence and the mixed audio, and then you have a separator framework. The separator framework is taking a 2D or kind of a 2D scene graph. I mean, it's a scene graph constructor on a single frame, and does the previous recurrent neural network business that I mentioned before. and it generates a separated audio. Now we add an extra constraint on the separated audio, saying that if you take the separated audio and then you pass it through a motion prediction, direction prediction network, the motion of the object in the visual space has to be predictable from the audio that you separated out from the mixture. So if you train it end to end, then the separator network induces some or modulates the spectrogram or the mask in some manner such that the direction gets encoded into the separated spectrogram, and then that can be extracted by this direction prediction network for predicting where the direction the object was moving just from sound. So we applied this pipeline onto the audio source separation framework I mentioned before, and we find that kind of improves the performance over the baseline. For example, AVSGS was the baseline that I just mentioned before, the previous work. And if you include the direction prediction module into the setup, that improves the performance more. And more interestingly, we find that just using, you can essentially predict the direction of motion or the visual direction of motion of the object that was producing the sound from the spectrogram. That is this 46.1%. If you did a majority vote, you get 27.3. So you have some directionality that is encoded within the separated audio that you can extract to predict the direction. So we believe that is an important, maybe, or useful thing that we could leverage for a lot of other applications in the future. So just to give an idea of what this is essentially doing, I have a small demo. So this is essentially doing the mix and separate framework. And the idea is that once it separates the audio from the mixture, we run this direction prediction module on top of the separated audio, and it has to predict a direction vector. Now it's audio, so you cannot really precisely say which direction the audio is kind of, or the object is moving. So you kind of create a cube, and you kind of want to predict in which coordinate of the cube this motion is approximately. So that's the idea. Oops. Yeah, so got the idea. So in the case of the baby sound, so we have 9 nodes in this graph, and you have a cube, and then 8 nodes on the corners, and then one is this middle point, which corresponds to no motion. And so there was no motion detected for that video. Now moving on, this is the last part of the talk. And so I'm going to talk about things by integrating the different modalities, including putting it on top of an embodied AI agent to navigate a scene. So embodiment has been a hot field in computer vision research lately. And there has been a lot of problems that we have been looking at through an embodied sense. For example, object navigation, where you are given a prompt, for example, find the counter, and you have to navigate the scene to find where the counter is, or pick and place where you want to go find some thing to pick up and then put it somewhere else. So, or it could be sound spaces where you have a sound being produced by some source at some location, and then you have to navigate the scene to come up with find the source corresponding to the sound. And so we have been kind of exploring this setup quite a bit. And one of the tasks that we thought is exciting and which currently doesn't exist in the literature is the task of audio visual language navigation. For example, in this sound spaces framework, just to put the context, you have a visual, there is an agent starting from position 1, and then there is a sound producing object somewhere in position 2, and the agent has to navigate the scene to find where the sound is coming from. And it could be a cell phone ringing in which it is a continuous sound. So you can use the sense of like whether you are going closer to the source or not to get to the source. But what if your situation is that your sound is not really continuous? Like it sounded for some time, but then the sound vanished, and then how do you navigate the scene? So one thought was, what if you actually included language into this navigation problem? So the agent starts from 1, and then it started moving towards a source, which is at 3. But then at some point, the sounding object stopped making any sound. And so then the agent can kind of go on with this estimate of the sound, location of the sound. Or what if it has the capability of asking a question or asking for help from a human? And the human provides a short answer or short instruction for the agent to navigate to a little bit later point. For example, in this the yellow the brown part marked, where the language instruction is given to the agent by some human who can see the scene, and the agent uses this language to kind of come up with a set of navigation instructions to go a little bit ahead, and then uses its own intuitions that it had before to reach the goal. So how can we integrate this sound spaces with vision and language framework to kind of make the agent learn when to ask a question or when to ask for help? So that was the task that we kind of thought to explore in this project. And so we came up with a deep multimodal hierarchical reinforcement learning setting for solving this problem. So the input to the system is a visual scene and its depth image. So you can see the scene and then walk through it. And then the binaural audio corresponding to the sounding source. And then other modalities that we could have on this agent. And the agent uses all this information and tries to, I mean, at every instant, it tries to do to answer the thing, like whether I should ask for help from a human. Am I confident to kind of navigate myself, or should so these two choices it makes. And if it thinks that it's not able to, or the uncertainty is so high that it cannot navigate by itself, then it switches to a vision and language module, which is a pre-trained module that kind of seeks help and gets an answer in natural language, which it can decode to create natural language instruction. I mean, navigation instructions, which then can kick off the audio-based navigation to kind of navigate the scene. And so it goes back and forth between whether the audio-visual navigation or the vision and language navigation to kind of explore the scene. So that's the idea of this multimodal hierarchical reinforcement learning that we built. And so I have a small demo to show what exactly it does. So on the left, you see the scene in front of the agent, and on the right is a flow plan, but the flow plan is not given to the agent. And also the agent has not seen this house or whatever, this environment before. So it has no idea where things are, where the sounding object is. It has to start from wherever it is and find the location where the object is making the sound. And at some point in its navigation, the sound producing object stops making any sound. So it's on its own to navigate until it asks for help. And the green is actually the shortest path from the source to the destination, but then agent doesn't necessarily need to take that. It can have its own ways of navigation. I hope you can hear the audio. It's some sort of like a shaking of the window in wind. Yes, yes. Yeah, at this point, the audio has stopped. So the agent has to still navigate the scene to figure out where the audio was from. And it gets confused because it doesn't have a reliable source of knowing where the sound was from. And it has given up. I mean, and it has asked for help. And so there is we assume that there is an agent somewhere who can see the scene and the state of the agent and give some natural language instruction. For example, in this case, go straight down the hallway. So then now the agent has to take up this this instruction, convert it into navigable actions, and then navigate the scene further. And it again gets confused and asks for help. And then it reaches the goal. And this was the window that was shaking and was making the sound. So it has reached the goal. So it's sort of like combining audio, vision, and language for embodiment and embodied navigation. So that was the task that we hope to solve in this. And we did a lot of studies to understand quantitatively how the performance is, and we find that the performance is better than not using language instructions. But then there is a significant gap between you interpreting the language for navigation and using the ground truth actions for navigation, because the language can be ambiguous, and how the system interprets what the language was saying and the actions it takes, there is a bit of uncertainty there that needs to be, that's one of the challenges that we hope to solve in the future. So that was pretty much what I wanted to talk about. So we explored real-world AI problems at the intersections of audio, vision, language, scene geometry, depth, and embodiment. And we showed how combinations of various modalities lead to elegant ways of solving these problems, often achieving state-of-the-art performances. And the backbone for most of these approaches that I presented was a scene graph. And scene graphs allow disentangling the scene into its constituents and allows better generalization and better and more sample efficient learning. Now, going forward, I think scene graph, the framework as such, has a lot more capacity to hold a lot of other modalities into a very highly integrative setup for higher level cognitive reasoning. So that is something that I'm trying to explore by integrating multiple modalities for solving a variety of reasoning problems. So that's pretty much it. And I thank a lot of my collaborators and students who worked on it to get this, to have this happen. And thank you so much.
Question? Maybe one question.
Yeah.
So the question I have is probably how do we know the ground truth of the scene graph? Right? That this is the correct scene graph that we are getting. And another thing, are these, like, do you see there are some limitations on the scene graph? Like, can they really model complex interactions more than say,
yeah. That's a great question. I mean, the first question, how do you know the correct scene graph? That's I would say difficult to answer. But then you construct the scene graph, and then the training process guides. So you are not really just working with scene graphs. It's just a disentanglement of the scene. Now, the graph neural network is essentially extracting the important nodes of the graph to create representations that are then used in the reasoning pipeline. So somewhere in between, the scene graphs are kind of changed or transformed into something be useful for the downstream task. It's sort of like any neural network that you start with an image, but then there is somewhere that things can get transformed. So the same thing happens with scene graphs, but that you're starting from a better the starting point, I would say, from a scene graph. And the second part, what was the second part? Like, so how do you kind of, limitations. I mean, the interaction, I mean, there are limitations. For example, these are visual scene graphs. And if you want to kind of do this across video frames, the dynamics, you cannot really capture the dynamics that easily with scene graphs, because some of these object detections are unreliable. The same object detected across different frames, there is no way to guarantee that the same objects are being detected. There's a slight occlusion, the detection goes elsewhere. So the tracking and I mean, kind of finding the correspondences across frames is a huge problem. But we hope that when we do this end-to-end training, all these kind of go away somehow, and the dynamics are kind of captured implicitly. That's the hope. But then I think that's just a hand-wavy way of saying that. But I would say, I think better ways of or more reliable scene graph construction is important in that regard. Yeah. Yep.
All right.
Okay.
Thank you again.
Thanks.